The first speaker is Michael Perlmutter from the Department of Mathematics at UCLA. And Michael is going to talk about audio enhancement via online non-negative matrix factorization. Michael, the floor is yours.
All right. Well, thank you. Well, thank you for having me here today. I'm really excited to speak at CIS. This is, since we want to be keeping on time, my talk is going to be about audio enhancement via online non-negative matrix factorization. So I'm going to begin by introducing the denoising problem and talking about non-negative matrix factorization, NMF, and its online variant, ONMF. Then I'm going to talk about algorithms for these methods. And then for the last portion of my talk, I'm going to talk about applications and results. So beginning with the setup for non-negative matrix factorization is we have data that is presented as a matrix X, and we want to factor it into two matrices W and H. And the interpretation is that every column of X can be written as a combination of the columns of W. So we view W as a dictionary where everything can be composed out of the columns of W. And H tells you how much of each W column do I need to make each column of X. So we call about this as the coding matrix. And we want this factorization WH to be as close as possible to X. And we could use a variety of loss functions, but in this talk, for the sake of simplicity, where it's going to focus on the Frobenius norm. And what really makes non-negative matrix factorization unique is that we are going to also add in the additional constraint that W and H have to be strictly non-negative, in the sense that every single one of the entries of W and every single one of the entries of H has to be non-negative. And so this is similar but different to a lot of other popular things. The basic setup is that every column of the data matrix can be represented as a linear combination of the dictionary elements. But the key is that the dictionaries have to be positive parts of the data matrix. And this could be in contrast to things like principal component analysis, where you might have oscillating dictionary elements with positive and negative parts. And the idea is that when you force everything to be positive, then there can't be positive numbers and negative numbers canceling out. And so because of this, what we'll see is that in PCA, you'll have dictionary elements which are globally supported and perhaps hard to interpret. Whereas in NMF, since there can't be any cancelization, this forces the dictionary atoms to be localized and therefore perhaps a little bit more interpretable. Like if you look at this thing right here, it appears to be the person's eyebrows. Now, in this talk, I'm going to be focusing on audio applications to audio. And the setup here is that we have somebody talking, but they're talking in perhaps a loud room, and the talk perhaps sounds something like this.
To be or not to be, that is the question. Whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against the sea of troubles, and by opposing end them, to die to sleep, no more, and by sleep to say we end, the heartache and the thousand.
And so the goal of this talk is to take that Shakespeare that we have and to keep the beautiful words of Shakespeare, but to get rid of all of the static. There also is a related follow-up project, which is my co-author's delivery was, maybe not as dramatic in its meter or its tone as we could like. And we are also working on a collaboration with the UCLA drama department to work on that, but that will be for future research. And today we're just going to work on getting rid of the static. In any case, mathematically, sound is represented as a matrix, a spectrogram, where we've got time on this axis and frequency on that axis. And the intensities of each of these pixels is how much of frequency X is going to be present at time Y. And we're going to try to apply non-negative matrix factorization to the spectrogram. And hopefully we'll come up with two different, hopefully we'll come up with some dictionary atoms corresponding to the signal and other dictionary atoms corresponding to the noise. Now, there's a lot of different algorithms for this. And one of the most popular is based on multiplicative updates. So what we do is we start with an initial guess of H and an initial guess of W. This is our dictionary matrix and our coding matrix. And then we iteratively update H by this multiplicative formula. Then we iteratively update W by a multiplicative formula. Then we update H, then we update W, and we go back and forth, back and forth, back and forth. And what can be shown is that the total error is going to be a non-increasing function, which will hopefully converge to something good. Now, this is a very popular method that's been around for a long time, but it's got a couple of drawbacks. And one is that it treats X as an arbitrary non-negative matrix that does not incorporate the time frequency structure in any way. Spectrograms are not just an arbitrary matrix, they're a special type of matrix where the columns are one thing, time, and the rows are another thing, frequency. So if we can incorporate that structure, we can hopefully get better performance. The other drawback to classical NMF is that you have to store the entire matrix in memory at the same time. And if our matrix is large, that's potentially expensive. So one of the ways to remedy this is with online non-negative matrix factorization. And the idea here is that at a given time, we'll take the entire matrix X, and then we'll take a small slice, a skinny matrix that has M columns, where M is much smaller than the total width of the matrix. And you can choose these columns in a variety of ways. One popular thing that really exploits the time frequency structure is you take a sliding window. So you'd have these columns here, and the next time step you'd have these columns, and the next time step you'd have these columns, and the next time step you have these columns, and it's a sliding window like that. The other thing, which is mathematically easiest to analyze, is that every time step you pick M columns, IID at random, or you can even do more complicated things where you would choose xt plus 1 as some random function of xt, and we'd model this by some sort of Markov chain. In any case, the idea of all of this is going to be that we have W0, and then let's just say we randomly choose X1. And then based off of this, we then choose the best H1 based on our initial dictionary W0 and our initial data matrix X1. Then now that we have X1 and H1, we then choose the best W1 based on X1 and H1. Then we keep iterating this, so we then would randomly generate another X2. And so now we have X2 and W1. So we choose the best H2 for W1 and X2. Then we would choose the best W2 for X2 and H2, and we would keep going in an iterative manner. And this is the intuition that leads to a scheme proposed by Merrill, Bach, Ponce, and Sapiro. And what they do is upon the arrival of XT, they choose HT to be the best code for XT and WT minus 1, where they also add in a L1 regularization to promote sparsity, because we typically want a sparse coding. And then they pick the best dictionary given all of the HSs for XSs, averaging over all of the XSs and all of the HSs up to time T. And this approach is very principled and can be analyzed with rigorous mathematics. But the downside of this is that computing this sum, where we're averaging over all XS up to time T, this requires to store XS for the first T time steps. So we're losing the memory efficiency. So to remedy this, we have a trick that says that you only need to store two matrices, AT and BT, at each time step. So in particular, we find HT the same way as before. HT is the best code for XT and WT minus 1 with our sparsity regularization. And then we compute WT via multiplicative update formula in terms of two matrices AT and BT, where AT and BT are aggregations of past information, where we're going to do 1 over T, and then a weighted average of our previous aggregation, and then just one new term that depends on HT and on XT to compute our BT matrices. The exact formula is probably not worth something dwelling on here, but the important thing to keep in mind is that we can compute these using just one new matrix, so we don't have to store T separate matrices, which would be an increasing amount of data needed to store at each time step. Or more formally, we get the following algorithm. At time T, we have a data matrix XT and a previous dictionary and aggregation matrices from the previous time step and some parameters. And so then we compute a sparse coding, we update the aggregation matrices, and then we update our dictionary. And what can be shown that was first done by Mariel Bach, Ponce, and Shapiro, and then later extended by Bolzano, Liu, and Nidal, is that if the data matrices are drawn in an IID manner, or even if they are drawn from a fairly general Markov chain, then this method will converge to exact reconstruction or to the best possible reconstruction. So shifting from the algorithm side of the talk to the applications talk, this has been applied to a lot of different mediums. In our paper, we talked about applying this to denoising, but here we are showing some previous work that applied this algorithm to images. So we have a nice painting by MC Escher, and we learned the following dictionaries from the Escher painting. And then here is something that we are able to reconstruct from our dictionary in a sparsely coded manner. Here we have yet another image and another dictionary. And here's a reconstruction from the dictionary elements. And another thing which is kind of interesting is here, this is another reconstruction, but here we are using the dictionary elements from the previous picture. So what we can see is that since these two reconstructions are different, we are learning different dictionary elements from different pictures, but they're, it does still somewhat work. And so perhaps there is some universal quality, there's some universal MC Escher dictionary where we can engage in some sort of a pseudo transfer learning, where you can take if you learn a dictionary on one MC Escher painting, then hopefully you can then reconstruct other paintings, at least by artists who tend to make geometric shapes in a Escher type manner. So again, our talk was based on spectrograms. And so here is the spectrogram of our original clean signal. Here is the spectrogram of the noisy signal. And it's worth noting that no, this was not a messed up picture. That it really is supposed to be gray like this because there is this intensity of about 15 that is present everywhere in the time frequency plane. But when we clean it up, either using traditional NMF or ONMF, it's going to look much more like the original, signal. And what we can see is if we focus in on this part of the time frequency plane, that right here, it goes from being relatively dense to relatively sparse. But down here, this is going to look much more like the original image. Now that's kind of fuzzy and qualitative. So we also looked at several quantitative measures, such as the signal to distortion ratio, signal to interference ratio, and signal to artifact ratio. And we did this both when the signal was corrupted by white noise and by real world noise. And by real world noise, I mean my co-author stood next to his air conditioner and blowed it on full blast while he was recording himself read Shakespeare. And what we can see is that high numbers are better in this context because it is signal to various bad thing. And both NMF and ONMF significantly improve the quality of the recording, but ONMF seems to work a bit better. And really to illustrate this, since audio is a very fun thing, and looking at a table of numbers first thing in the morning is perhaps a little bit best fun, we should maybe listen to the noisy recording.
To be or not to be, that is the question. Whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against the sea of troubles, and by opposing end them, to die to sleep, no more, and by sleep to say we end, the heartache and the thousand.
And now that I've played the noisy recording twice, and Shakespeare's probably rolling over in his grave, we can now listen to the slightly better recording.
Not, that is the question. Whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against the sea of troubles, and by opposing end them, to die to sleep, no more, and by sleep to say we end, the heartache and the thousand.
And that is where I'm going to stop. Although I would like the final addendum that Andrew pretended to lose the recordings of him reading Shakespeare, but our other co-author was able to conveniently find them, and therefore I was sufficiently able to embarrass him in front of the audience.
It sounds like these stories about the previous administration. but thanks a lot for the nice talk. I have a very quick question. So because maybe I'm bringing my engineering background, so there's lots of work in signal processing on removing noise and dealing with noise. Have you tried to compare this to maybe just have like some filter, some linear filter, or these kind of things?
We did not compare against linear filterings. It is worth noting that NMF-based methods are no longer state of the art in denoising. My understanding is that they were at least very popular about 10 years ago, and then, like most things in life, they've been displaced by artificially intelligent robot overlords and various deep learning methods.
Yeah.
That said, we still do like NMF because of the natural interpretability, and really our focus was to show that the online non-negative matrix factorization can be done to improve NMS-based methods because it respects the time frequency structure. And there's been a few different works on this. What we did is we were focusing on a Frobenius loss function. And the nice thing about this is the theoretical guarantees that I mentioned in this talk here. These theoretical guarantees, which I did not state formally because it's a 15-minute talk and that might have taken 20 minutes. That these theoretical guarantees with this loss function are more general and have placed less restrictions on the data. So we wanted to show that can work well. But if we were truly after just brute force quality, we probably would use either deep learning based methods or possibly a more sophisticated loss function, which would be harder to analyze mathematically.
So I think we have time for one very quick question, if anyone of the audience has a question. So Benedito.
Yes, great talk. I really like your talk, Michael. Good job. Just a question. So the spectrograms, they do not capture phase, right? And yes, it does not make much impact in audio, but I was wondering if, I guess the fact that you need to enforce negative, so that's real matrix is W, right? So I wonder if you could try to extend this. I wonder if phase would end up giving a little bit more better performance? I don't think so, but just a food for thought, I guess.
So I mean, we just wound up. I mean, so we just wound up piping this into to a standard phase retrieval algorithm, which I think that there's, I guess, yeah, I'm not really sure what, I think the issue is that when you add noise, the noise tends to affect the phase quite a bit. And so if we incorporated the phase, that could make the denoising more challenging. And so we prefer to just ignore it and then pipe the end result through a standard phase retrieval algorithm. I think it's something like a Giffen-Lamb or something like that.
Yeah, I see what you mean. Phase, I guess the fact that you're not recovering the phase, not only you, but any algorithm that does disregard the phase, in a sense, you're never recovering the true signal, right? But I see your point that, yeah, phase is in audio, phase we usually can disregard. Great talk again.
Yeah, thanks a lot, Michael, and thank you, everyone.